I want to go back to a conjecture that we had for all the generic Painlevé equations. So suppose, and you've seen that several times in my talk, so it's been one of those things I've been looking at for a long time. So our distinct solutions of a generic Painlevé equation then transcendence degree over C of t of a differential field generated by the solution over C2 is 2n, right? All right, so
is that the differential field generated by?
So I'm going to say a few words about it. Thanks. So usually the form written there is what's called the Hamiltonian form, but there's also a form of a Painlevé equation which is just a second order first degree. Second order first degree differential equation, and so usually when one talks about the Painlevé equation, one think of this system, and so for those who've seen the 6 of them. But once you go into the proof, it's usually more useful to work with the Hamiltonian form. All right, so there's a way to go from here to a second order system. All right. And indeed, that's... Yeah.
Sorry. No, I'm sorry.
No, go ahead.
How do you define generic again?
Yes, so for example, the alpha, all the parameters...
Algebraically independent?
Yes, so the alpha, beta, gamma, delta, or the alpha node, alpha 1, alpha 2, depending on which form of the equation you're looking at, are algebraically independent over Q. All right, so this was sort of yeah, the algebraically independent. So transcendental constant, and so this being an ongoing problem, which I started in my thesis, but the first person who really answered that part of it is for P1. So true for the first Painlevé equation. So I'm not writing it down here, but some of you might remember, and that's a work of Nishoka.
Question.
Yes.
Is it, remind me, is it true that the Painlevés with smaller numbers are in some sense special cases of Painlevé 6? Or am I misremembering?
So it is, but not differential algebraically.
Okay.
So there's a way to get from one to the other, but it's not a differential algebraic sort of process, right? Yeah, computation. Yes, yeah. So
for the Painlevé 1, does it also have 4 parameters that are going to be?
So that's an interesting thing. So Painlevé 1, let me write it here.
I'm happy not to see the actual equation.
It's easy.
No, it's easy, right? So it's not. There's no parameters, but it's if you think of you consider it generic in its own on its set, right? So that's and all the others have parameters, and you're really talking.
So no, actually, then a question: what does generic mean? Is it generic in the sense of
that's a
generic in the family? So if the family contains
no, but generic in the sense of culture closed, generic in the sense of
no. So this is constants, right?
Not.
Those are constant parameters.
Right, but there are no parameters there.
So you have P2 has one parameter.
No, so wait one moment. So for this conjecture for P1, what does generic
Yeah, so that's what I'm saying. So it's in its family, it's only itself
it's the only
in the family,
one, so it
right?
is it's
it's generic in them, right?
Okay.
Whereas the others have many members of the family.
P1 doesn't need generic.
It's not distinct generic solutions.
There.
It's distinct solutions of a generic.
Of a generic, yeah, exactly. Yeah.
Okay.
All right, and so then we had some sort of breakthrough.
So the solutions don't need to have any independence?
No, so that's, as stated, and indeed we'll be talking about differentially closed field. So take n solution in a differentially closed field, as long as they're different, that's going to be true, right?
Yeah.
So we call that strictly disintegrated. And so for P2, P4, and P5, sort of, that was work with Anne and so this was a sort of breakthrough, and we sort of managed to use model theory to prove that result. And whereas Nishioka uses very much computations, so usual computations when you try to prove things are algebraically independent. And so if you remember, Dart, I talked about P3, that I've managed to do that as well. And it was very specific to the third Painlevé. So today, I'm going to talk about P6. So true for P6, right? But interestingly, the proof can be used for all. Except P1 of because P1. So it's just a question, if you have generic parameters, it's a question of specializing the parameters and looking around. And also, another perhaps an interesting thing is Nishioka's technique is used. All right, so somehow with P6, you have to have some computation, but it's not done to the level of the Painlevé equation. It's done to a level of Riccati equations. So which I'm gonna say a few words. And so, so if you've seen talks either of me and Anne about the generic Painlevé equations, so the main idea is to sort of specialize the parameters, specialize to non-generic parameters. So we have a way to, it's generic and sort of a way to go down to non-generic parameters, and then in this case is to solve and reduce the problem to Riccati equation. So again, if you remember a little bit my talk in Dart, that's already something I did, yes.
Is this, there's no condition on n?
No. So for any n, any number of solutions.
Yeah, so here's something that I didn't know. If you have a generic Painlevé, there are no proper subvarieties?
No.
Ah.
That's
so you don't
used
get
in
the
there.
order one?
Yeah, that's used there. And indeed, the order one, we will use the order, those that have order one subvarieties, we will use them. That's what I mean by specializing the parameters to where they are.
But for the generic,
But for the generic, there's
there
none.
wouldn't be any.
Right. Yeah.
Oh,
Yeah.
okay. Huh.
And so, yeah, as I said, if you remember, some of you might remember how it went in my Dart talk is, I indeed did that. I sort of started from generic, went to Riccati equation. But then it was very specialized. So the difference, the difference is, what's new is, we obtained a general transcendence result for Riccati equation. And that's where Nishioka's technique is used. And so if we have some general result about transcendence of the Ricardi equation, then when we specialize, we are able to get the result. Yes.
Can you say 2.5 words about who the Ricardi equations are and what their place in the world is?
Yeah.
Do you mind waiting a little, because there's going to be a full
Okay, great.
part about the result,
Okay, great.
right? All right, so what's my plan? Maybe we can write it here. So the plan is, I'm going to say a few words about strong minimality. Just for those who are not model theorists and need to be reminded what it is and some consequences. And then I'm going to talk about Ricardi equations. And then I'll say a few words about the proof. And if everything works fine, there's no clock anymore. I should be able to say something reasonable about the proof as well. All right. So let me start with strong minimality, and I think it's almost. All right, so UD will be a universal differentially closed field of characteristics 0. Looks like a 6. And so C would be the constants. So field of constants, and T will be a fixed element that acts as a time variable, so fixed element such that.
So C is the constant of U.
Yes, so constant of U. So C would be y in U such that dy equals 0. And so I can sort of do that by putting an assumption, let's say, on the cardinality here of U. Let's say it's continuum. The field of constant has to be continuum, and so I can identify it with a complex number. Right? Okay, so take X definable set over K. So X is strongly minimal if every definable subset, so with extra parameters, if need, with possibly with extra parameters. So if every definable subset is finite or cofinite. So either it's finite or the complement is finite. And so straight here, just from this definition, C is an example. So in U, every definable subset will be given by a polynomial equation or polynomial equation in one variable. And so either it's going to have finitely many solutions of polynomial, or if it's an equation, it's going to have everything else. All right, but sort of, let's differential algebraically. There's a nice characterization. Say X is given by y prime prime equals f. So let's say yn equals y prime yn.
N minus 1.
N minus 1, thank you. Where f is rational over C of t. So like the Painlevé equations, or then so you have an x is strongly minimal if for any k differential field extending C of t and any y in x, you have at the transcendence degree of k y over k is 0 or n. And this means that either y is in k alg, so algebraic over k, or y is generic, k generic.
So basically what you're saying is that differential varieties given by equations like that are automatically irreducible.
Irreducible, yeah.
And once they're reducible, being strongly minimal is the same as having no proper subvarieties.
Yeah, exactly. Yeah. All right, and so again, so for those who are not too used, if you have a solution, then for over any field extension that's in U, either your element will be algebraic or it will have transcendence degree n. So there's no subvarieties of order, let's say, any lower order, right? And so this is related to what you were thinking about. And so, for example, Rick A, B, C, so not our Rick here, but the Riccardi. So y prime equals A y squared plus by plus c. So this is a Riccardi equation where, let's say, A is always not 0 and A, B, C are in C of t. All right, so this is an example of something that's always strongly minimal. The reason being it's an order 1 equation, and automatically everything will either be 1 or 0, right? And so and that happens for first order equations that are of this form. All right, and yeah, I thought I divided, it would be enough, but I forgot to divide here. So, and also, all the generic Painlevé equations.
But that's already a serious theorem, yes?
Yeah. I just pointed out, it's not an easy thing to get, right? Proving that there are no order 1 subvariety, and indeed over any differential field extension takes some work, and so these are results of, so you have Umemura, Watanabe, and of course they don't quite know moral theory, so translated was part of the work with Anand, so trying to figure it out that actually what they were trying to prove was strongly minimality. All right.
What do you know about non-generic Painlevé?
So that we have more. The results are a little bit better than that. So
okay.
Let me spend maybe 2 seconds to say that. So I'll do it here, but next time the division is going to be perfect.
And also Coltrane's then should be there.
Sorry?
Coltrane also for...
Yeah, for first Painlevé one. Yeah, exactly. Yeah. So indeed, after Coltrane sort of did that, I think it was in something he never published, but part of the work was revived by Umemura Watanabe after sort of seeing Coltrane's work on P1. let me just. So let's look at P2 alpha, which is y prime prime equals 2y cubed plus ty plus alpha. All right, these are the only two Painlevé equations I can write. And so, for example, not only do we know generic parameters that they are strongly minimal, we know that strongly minimal if and only if alpha is not in a half del C. All right, so we know precisely where it's strongly minimal, and it's always fun to write them. So, for example, where alpha equals minus, let's say, half, you have y prime equals y squared plus t over 2 is a order 1 distant variety, right? And you can see that if you differentiate one more time, you have 2y y prime plus half, and it's 2y y squared plus t over 2 plus half. So you end up having the third Painlevé equation with parameter half. So this is an example of order 1 a violation to only having 0 or n. Right. Okay. And so I also want to, so this is sort of important. There's sort of something better than strongly minimality in some ways. So suppose x, k definable is strongly minimal. Then x is, let me say, k reducible if it has no solution in K algebra. And so you could, the idea, so this is, again, part of the work of Memura on irreducibility. So there's a reason why it's called irreducibility here. For example, let's say the Painlevé equation are defined over C of t. So once you don't want to have order 1 subvariety, but then you also want equations that don't have algebraic solutions over C of t, right? And this was due to Painlevé idea that the Painlevé equations are sort of new special function. So it's not going to be algebraic functions over C of t, or it's not going to be any sort of first order solution to first order equation. And from the sort of mole theory side of thing, it's important that because if x is k reducible and phi x is KLK formula. So a formula in the language of differential ring where you have parameters for k. Then if phi is true of one solution, it's true of all solutions. And so if there's a first order statement over K that holds of one solution, then that statement will hold for all solutions. Yes?
I think I missed it. This notion of K irreducible, is this a definition or is this a statement?
It's a definition. So it's a definition, right?
Okay.
Indeed,
so it doesn't particularly match the usual definition of being an irreducible.
No, so it's not the Colchin irreducibility or not irreducibility in terms of variety. It's a sort of, again, so Painlevé wanted to say that these are new functions, and Umemura came up with a notion of irreducibility to describe that. And you can see that equations that are K-reducible means they have no solution. Strongly minimal K reducible means they're quite solutions are quite generic in some ways, right? And that was the idea. But for us, this is sort of important in that this is used in many of the proofs that we have on the Painlevé equation. So in particular, all generic Painlevé are CT irreducible. All right, so they're strongly minimal, but more they don't have solutions that are algebraic over C of D.
What's an LK formula?
Simply take the language of differential ring.
Oh, it's the language is differential algebra?
Differential ring, and add constant symbol for K, elements of K, and then start writing any kind of formulas. Right.
DCF.
Mm-hmm.
0.
All right, so perhaps let me just maybe point out something about the Painlevé equation before moving to the Riccardi equation, and then we'll come back to that. Actually, let's move on to the Riccardi. All right, so this is sort of just a brief recap of strong minimality and sort of K reducibility. So let's look at the Riccardi equation. Right, so from now on, Ric ABC is, again, I'm going to write it again, y prime equals x plus by plus c with c, so a not 0, and a, b, c in c of t. All right, so that's going to be my Riccardi variety. And so I would assume that Ric ABC has no solution in CTH. So basically, CT irreducible. Right, so perhaps before saying more about them, so why do I allow myself to do that? So let's look at the 6 Painlevé equation. So remember we have x6, alpha, note alpha 1, alpha 3, alpha 4. Alpha 2 is given once you've got alpha note of the others. And so when alpha note is 0, right, what you have that check y equals 1 gives Riccardi All right, so it takes maybe 1 minute to just, y equals t, sorry. Put y equals t and sort of, you see that everything clears up, and perhaps let me write it down. It's not pretty, but so you have y prime equals 1, and x prime equals minus x squared plus alpha 3 plus alpha 4 minus 2. The details are not too important, but you'll be able to work this out in no time. X minus alpha 2, alpha 1 plus alpha 2. All right, so you have sort of a Riccardi subvariety when alpha naught equals 0. And so the point is that all these, I would say all these order 1 subvariety that appears as, so all the Riccardi varieties that appear have order 1 subvariety of Painlevé equation, this one, they all have no algebraic solution over C of t, right? And so this assumption is strong, but it holds for many, many examples of Riccardi variety. And they hold for the Riccardi varieties that I sort of really care about. All right, so the transcendence result I'm going to prove about these guys holds only when C of t, it's CT irreducible. All right?
Are there any other values for alpha naught where you get something?
And so it's going to be exactly like what we did there. So you'll apply definable bijections to get that there are not Riccardi varieties, but order 1 subvarieties. So for example, here, how did we go from, at alpha equals half, we have a Riccardi variety, but we said that it's strongly minimal as long as you're not in half plus z. Well, you're going to transform, you're going to apply what's called background transformation to these equations, and they're going to give you, for the 1 subvariety, for this entire, in this entire set.
Yeah, what interests me about this is, well, in Jerry's algorithm, when you have a second order equation, you're looking, he looks for solutions of the form e to the integral theta. And it turns out if you satisfy the second order, but you satisfy the second order equation if and only if theta satisfies a Riccardi equation.
Yeah.
So you're looking
at second order linear.
That's right.
Linear.
That's right.
Yeah. And indeed, I'm going to talk about the linear equation in a second. Yeah. Yes.
When you and then the condition that the alpha naught be in a half plus z looks very much like in that's the same condition you get in the Bessel equation for the group. The group being SL2. Well, if you write it in with the what I call the normal form, when you don't have a viscosity term, then it's exactly that condition that the group is.
That's an Aries equation.
It's
interesting. So I don't know whether there's a connection.
It looks very similar.
Yeah, that's right.
Right, and so
I wonder if all the Riccardis and all the Painlevés come from Aries or Bessels. In other words, SL2 is the relevant group.
Well, you got to worry about that viscosity term because Jerry just eliminates it right away.
Oh.
On the other hand, you from that you can get back the original information.
It's pretty easy to get into SL2 and then
All right, so now this is sort of the assumption I'm working on in that section. So bear that in mind. So some facts about the Riccardi. So most are well known. I mean, I think all are well known. So the first one is the map take y, the map y goes to ay is definable bijection between the Rick A BC and RS, I guess. Yeah. RS with where the relation is R is B plus A prime over A and S is A times C. All right. So the first one said there's another form of the Ricardi equations that you could sort of look at and it won't change much and things that so we will care about. And secondly, this one is so and also note that Rig 1RS also has no solution, is CT irreducible. All right, so we started with Rig A, B, C have no algebraic solution over C of T, and you have a definable bijection. So the one you end up here doesn't have algebraic solution as well.
So that's what you always mean by CT irreducible, no algebraic?
No algebraic solution.
In this context?
In this context,
Yeah.
right? So yeah, I'm sorry, it's sort of a, and again, so even for us when we saw that they had a notion of irreducibility,
Yeah.
it sort of was in the way of already existing notion. But in this
Yeah,
talk, I'm
in
only
this
going to talk about CT irreducible, meaning
algebraic
that.
solution.
Yeah,
Okay.
yeah. And okay, so here I use the fact that I said already, Rig ABC is strongly minimum,
Right.
right? And so.
Right.
So that's why I call it CT irreducible now. Wait. Maybe I should find a different term to.
Yeah, you should find a different word.
Put down strong minimum.
Anyway, so
So whose notion is this?
it's Umemura's notion.
So just call it reducible.
Yeah, so that's what we actually did in our paper. So let me just say CT U irreducible. Is that
Okay.
again for U for Umeru? And that's how we call it.
Oh yeah, we're reducible.
Sorry.
We're reducible.
U irreducible. Yeah. Maybe make it a little bit better by saying
Irreducible.
U CT irreducible.
No, that's not actually right. The U definitely goes after the CT.
Yeah, I know. But to make it easy, I'm gonna say
How about
How about we go back to the...
irreducible.
No algebraic solution.
Let's not worry about this
yeah, let's not worry about
Okay.
it. So CT
at this point.
U
We can
reduce. Irreducible.
What we call it?
I must get confused at every step.
Well,
Yeah, exactly. So I'm gonna put the U everywhere so that there's
Okay,
no.
great. Thank you.
And so,
that's for the universe.
and the second fact is, so consider U prime prime minus, so the linear differential equation, what that Rick was pointing to. So consider the linear,
A, B, C.
yeah. So let's call that
Oh, an R in there.
curly L R
R's.
S, right?
Ooh.
So that's a definable set given by that. Then, for any solution, for any y in Rig 1 or S, there is U in curly R S such that y is u prime
Curly L.
Curly who? Curly who? Curly C?
L.
Curly L.
L.
Curly
Curly
L.
L.
So that's just a statement.
Yes, that's the one. So for any solution of the Ricardi variety, what we have there, let's say, you can sort of have you have a sort of definable map to the.
And is it also true that for any solution of the linear equation, the log derivative will be a solution of the corresponding Riccati equation?
Only if it's of the exponential form.
Yeah, exactly. So that,
So not all. Okay.
not all. Yeah. And here, so I mean, it's
It's
easy.
a rank 2 set, right?
Yeah, that's
Rank 2 set.
right.
Well, rank 2 can map to a rank
Rank 2
1.
Morley
It's
rank?
just not
Morley
1 to 1.
rank?
Yeah.
And so to see that, not a proof, but easy. So let u take u in curly L RS, then easy to see that u prime over u is in Ric 1 RS.
Ah, so that is what I was asking. So you're saying that for every solution of this particular linear equation, its log derivative
Oh yes,
is in the
yeah,
solution.
yeah,
Okay.
yeah.
Okay.
So if you take a solution and you
Yeah.
you differentiate, you take the log differentiation, it is a element of a Ric, and so let's call this Z, and now you can use K reducibility. You can say there is U such that Z equals U prime over U. That holds of Z, and this is a CT, this is given by a CT, LCT formula, and it's holds of Z. Let me call it alpha to make sure that it's not a, right? It holds of alpha.
That's nice.
Then, because it's CT reducible, it'll hold of every element,
You get surjectivity.
right, in your set, right? And so this is an example of how one uses this CT irreducibility. CTU irreducibility.
Ronnie, I lost what curly L actually was.
Oh, it's the definable set given by that, right? So it's a linear,
Well,
L for linear.
Oh, L. Oh, I thought L was a field and a join all.
No. L is for linear. That's why it's not a normal L, it's a curly L.
That's the solution set?
Solution sets. Yeah, so because I work in U, the usual identification, when I talk about equation, I'm only looking for solution in U. So I can identify it with...
We don't use that symbol. I'm not used to it.
which symbol?
L of RS for the variety.
I actually use it to make it easier because this says linear equation, but I could put a V if you wanted.
Okay.
Ric is to say that it's a Ricardi.
Yeah,
L is to say that it's linear.
That's good,
Is that okay?
Yeah, got it.
Your generic condition is excluding a lot of solutions that,
Yeah.
of that.
Exactly.
Oh, okay,
Right.
okay.
Exactly. And so this is I guess CT reducibility is a strong condition in that way. All right. Probably need to speed up a little. I think I'm okay. All right. And so we will use this to show something, but to note that so if we fix two CT linear independent solution, U1, U2 of the linear variety, then any y in RIC R1 or S is given as y equals u prime plus a.
U1, U2?
U1 alpha is not good, so let's say C is not good, let's say gamma U2 prime over. Alright, so there's a gamma. So basically, once you fix a fundamental system of solution of your linear equation, you can describe all of a solution of your linear equation that way.
So you're projectivizing the solutions.
In some sense, yeah. But really, all I'm using is I fix a fundamental system of solution.
That's you.
Oh,
Then all of the solutions of this guy is going to be of the form u1 prime.
And those are derivatives.
And then the derivative, the log derivative would be a
Gamma is a
solution.
constant here.
Yeah, that's a constant. Yeah,
What's gamma again?
a constant. Thank you. Yeah.
So this tells you that the Riccati equation is tied down to the constants very tightly.
Very tightly, yeah. Yeah, and there's another way to see that, and I'm going to say that in a second. And indeed, so it's strongly minimal, but it's non-locally modular, right? All right, so where am I going with that? So let me just say proposition. So let y1, y2 be in RIC A, B, C. Right, so remember they are, it's CT reducible. Then transcendence degree over C of t of y1, y2 is 2 over C.
I guess you at least assume that they're not equal.
Distinct. That was the next thing I was going to say. Yeah.
Distinct.
So if you take distinct solution of a Riccati equation, all defined over C of t, which is CT reducible, then you have that the transcendence degree is two solutions too. So they are algebraically independent over C of t. Now, this is probably not as far as one can get. One could try to look at 3 distinct solutions, right? But the reason why this is sort of, I was looking for such result in the literature, and I couldn't find anything about independence of solution. And the reason, I guess, why this has never been looked at is because well known that another way to witness that it's non-orthogonal to the constant is if you fix y1, y2, y3 distinct in RIC A, B, C, then any third one
Any fourth one?
any fourth one is given in terms of these 3 with a constant,
Constant.
right?
Cross ratio.
Yeah, cross ratio, exactly. Then for any y in RIC A, B, C, you have that. Do I want to write that down? Yeah. Y is gamma y1 minus y2 plus y1 minus y2, y2 minus y3.
Yeah.
And indeed, this is taken from Phyllis's notes in the KFT.
Already differential equations book. Well known.
Where gamma is in C. All right, so once you fix 3 distinct you witness non-orthogonality to the cost. So this is a sort of superimposition law.
I guess
Yeah.
you sort of know that because once you fix two solutions of the underlying linear equation, then you have at most 4 transcendence degrees, and now they span
Yeah,
the
yeah,
solution space
exactly,
for their
exactly.
property.
And so this is a sort of if you know non-orthogonality or internality, you can always witness by finding a sort of fundamental solution of your own solution set. So this is kind of a realization of that for the Ricardi equation. But the point is, it's well known already that you can't do better. You can't take 4 solutions and hope to have they are algebraically independent.
So the only question is if you take 3 random.
Exactly. So 3, 1 can sort of wander as well.
Yeah. Is that for any Riccati, the proposition?
The proposition is for, again, any Riccati where I need CT U irreducible.
Oh.
Right? So as I said, so it's a very sort of general result.
Doesn't the proposition?
Because the well-known is true for all.
Yeah, this is true for all.
I mean, maybe
Right.
A unequal to 0 or whatever.
Yeah, A shouldn't be 0. Yeah. And again, so A, B, C, my fixed data, where A, B, C are in C of T.
Stupid question.
Yeah.
So the content of the proposition is to say that it's at least 2, right? Because Riccati is an order 1 equation, so it's at most 2. Always.
1? It's most.
No, I'm asking.
Most
No,
one.
it's 2. So CT reducibility
Oh, for 2 people.
get rid of the possibility of having
1.
1 by stupid algebraic reason. So here the proof of content is that if you take 2, they already are going to be non-generic over C of T. Because it's CT reducible, there's no CT algebraic solution.
Wait, but the
The variety
So
has
we
to
are-
mention
I
1.
mean, the equation forces that looking at the field generated by y1 and y2 is the
Yeah.
same as the differential.
Yeah, it's the same as the differential.
That's right.
but
Oh, that's
yes,
good,
the
that's
equation
good.
only
Mhm.
enforces that, right? So
It's
the
like y prime. Yeah.
Sorry, I'm
Yes.
being very stupid.
No, that's right, so let me-
No. So
It isn't y prime.
Let me try to
So
say.
the conclusion in the proposition, it says that then this transcendence degree is equal to 2.
Yeah,
If we didn't know this proposition,
it could be 1 or 2.
it could be 1 or 2.
Yeah. So I'm saying if you take any 2 distinct solutions, they are going to be algebraically independent.
So does that not follow from the well-known thing? Because if you take any 2 distinct solutions,
No.
you can always add a third distinct solution, and now they have to span, the 3 of them have to span everything
Why?
by the well-known statement.
How?
How though?
Say that again?
So you give me y1 and y2, and you want to rule out the possibility that they generate a field of transcendence degree 1,
Yeah.
right? So I'm going to pick up a third solution of the same equation that is distinct from your first 2, and now put these 3 into the well-known statement. Now these 3, via this
Yeah,
this
they do
formula,
that, right?
have to be able to produce all the solutions of the Riccati equation.
Yes, that's true.
So could
Yes.
Yes, they do. Every
Does
y
that, would
has to
that
be
not
captured
immediately
with that.
contradict
Oh,
the
this is
dependence of the
something
first 2?
differential? That's
So how you would contradict? Let's see.
Maybe not that
Yeah.
much. I'm just trying to think.
Why do you know necessarily that just like one of your first 2 and the new one don't span?
Well, so I guess
So somehow, it'll be interesting to
depending
think
on
about
what
that.
they see.
Let me think. So you take 2. You have
Which way?
this one. You have the third one.
See.
Well, so perhaps.
Then you can always get a third.
But perhaps it doesn't say anything about how why shouldn't we be able to generate the entire solution? Perhaps that's a question.
Yeah, okay, that is the question.
Quite cool,
Yeah.
right? And so this would tell you that you need 3.
Uh-huh.
Right?
Because if 2 could generate, then you take. Wait, why does that tell you?
Yeah. Well, I want to generate everything.
It tells you that 1 can't generate.
Oh, because if you take a third one,
Yeah?
so you could fix the 2,
Yeah.
and then take one that is not.
Take 2 and
Yeah, it's not gonna tell you that probably.
Okay, but
But what I'm saying is, we don't know that if we fix 2,
Okay.
we can't generate
Okay.
anything, right?
But the one thing that this proposition does tell you is that if you fix 1, you can't get
Yeah,
the
you
rest
can't.
of
Yeah,
them.
exactly,
Okay.
exactly. Yeah,
Interesting.
yeah,
Okay.
yeah.
Okay. Thank you.
Thank you. And that's a very interesting point. And
yeah.
so perhaps proving 3 as well would be a nice result on its own, because then you would say that you actually need
Yeah, that would
3
be
solutions.
shiny.
Yeah. Yes. All right. Yeah. So. What do I want to say about this? Maybe a few words about the proof. It's a two-step, right? So first, we prove a lemma.
Is this the proof of this proposition?
Yes, proof of the position.
Okay.
Let's call it prop 1, proposition. So first we prove an intermediary lemma, and that's where one uses Nishioka's technique. So suppose y1, y2 are in RIC 1 or S distinct. So again, I'm thinking of the same assumption that R, S are in C of T. It's C of T reducible.
So you're proving it just for RIC 1RS, not for general?
That's the lemma.
Oh,
Right? That's the lemma.
Okay.
And then, but then you can see how if it holds of RIC 1RS, then it has to hold for that one, because there's a definable bijection with RIC, right? And so if this one had transcendence degree 1, it forces this one as well to have transcendence degree, right? So take that distinct then. If, let's say, y1 is in, let's say y2 is in C, T, y1 alg. So if it is algebraic, then it's definable. Right, and so you can't have algebraic dependence. If you have algebraic independence witnessed by a polynomial, it's already sort of witnessed, it's already rational, all right?
Yeah.
And now this is sort of
Yeah.
adapting Nishioka's techniques, right? And the way one does that is you use the fact that y2 in